Good evening and welcome to this live interactive problem solving session for the NPTEL course Transition Metal Organometallic Chemistry Principles to Application. So in this series of discussion I have already covered week 12 problem solving session in last week. And each week session I have discussed about more than 10 to 12 questions related to this week content. So today, if you have any doubt regarding the overall course content or any questions which has been discussed, I will be happy to answer that, or I will try to answer that, or if not, then today I will start discussing the summary or important point of this overall course. So today this session is going to be a summary session where I will try to go through all the slides which have been shown in the lectures, and I will point it out some important topics or important reactions which need to be remembered during examination. So if you have any doubt, you can directly ask me, or I will start discussing the today's session with just the summary of this overall course. So as from the week 1 to week 12 I have already discussed that is more than 10 questions in each week, that is about 120 or more than that questions I have already discussed. It is all the questions are already uploaded in the recording sheet drive. You can go through it for better understanding each week content, and you will get the solution in the corresponding YouTube link. So as the last day session I forget to turn on the recording, so I recorded that session again without the live interaction to get the answers, or so that everyone can get the answers of questions which was discussed during the live. So I ask anyone, if anybody have any doubt discussing, I will try to discuss that. So today I have this original slide which is shown during the lectures. So I will go through quickly in all the slides, and I will stop at different reactions or different points which I will discuss quickly as a summary of this course. So today this session is going to be a only summary session, or if you have any doubt you can ask me. So today I will not going to discuss any other questions, new questions from this topic, because 120 assignment already is there in the portal, and more than 120 I have discussed in week 1 to week 12. So now I think this 250 question is enough for understanding the course content, and solving that will give you a strong idea of this topic, transition metal organometallic chemistry principles to application. So if you have any doubt regarding this content, you can ask me, or I will go through the slides one by one and discuss some important points. So before the exam, I suggest you please go through all the questions which has been there in the main portal, which has been solved in weekly basis. Also, please go through the questions which I have discussed during the weekly problem solving session. This session, that is the today's session, is an extra session for summarizing the overall course content. Or if you have any doubt regarding any questions, I will be happy to discuss that. Okay, then I will try to discuss the overall content of this course, Transition Metal Organometallic Chemistry Principles to Application. So in this course, mainly we have discussed the different transition metal organometallic compounds. So if you ask me to classify this course in major parts, I will classify it in three major parts. So first, transition metal organometallic compound means where transition metal is bonded to a carbon atom. So depending upon the hybridization of this carbon atom, we can classify this course, the overall course content, in three parts. First, we have the transition metal organometallic compound, that is the transition metal bonded to the carbon atom, which has sp3 hybridization, that is transition metal alkyl complexes. Next, we have transition metal bonded to a carbon atom where carbon atom is sp2 hybridized, that is called transition metal vinyl complexes or transition metal carbene complexes. So there are variety of ligand having the where carbon atom having sp2 hybridization is bonded to the metal. And lastly, the transition metal attached to the carbon atom where the carbon is sp hybridized. So depending on these three criteria, the last we have called is transition metal carbene complexes or alkyne complexes. So depending upon this broad classification, we have a general idea what we are going to read in this overall course. So in this slide we have seen that the electronegativity changes with the hybridization. So depending upon the different electronegativity of different carbon atom, will have the different bond state when these carbons are binding to these transition metals. As the same way, the order of acidity, as we all know that it also varies on the hybridization. So the sp3 is electronegativity is least, whereas sp electronegativity is highest. So these determine the bond strength or the bond energy of a transition metal carbon bond. So transition metal alkyl complexes mainly form with the alkyl group. Alkyl means these are the small aliphatic groups. So, and these having the first we need to determine or know the stability of these complexes. So these transition metal complexes follow a very well known or established rule, that is called the 18 valence electron rule. This 18 valence electron rule suggests that the transition metal complexes having the total or overall 18 valence electron per metal center is highly stable in nature. Depending upon the number of electrons or total valence electron, we have classified these complexes in class 1, class 2 or class 3 compound. This classification is very easy. Now this 18 number is coming from this 1 plus 3, that is the 4 orbital corresponding to the 8 electron of Ns and Np. So this is Ns and this is Np, and this 9 is corresponding to the n-1 d, Ns and Np. So 5 from the d, this is S and this is P. So this gives rise to 18 valence electron rule and gives rise to the stable electronic configuration. Depending upon the coordination number around the metal center, this 18 electron complex may be, or sometimes the less than 18 electron complex also gets stabilized. So the 18 electron is no valence electron is not only the only criteria for stabilization. Sometimes the 16 electron complexes also get stabilized. So depending on the number of valence electron, we can characterize the compound. Also we can determine or get a general idea about the reactions of these transition metal complexes. Generally, the less than 18 electron complexes undergo the substitution reaction via associative mechanism, whereas the more than 18 electron complexes undergo the reaction via dissociative mechanism. So the properties of these transition metal organometallic complexes can also be entertained by these 80 electron rule. So this rule is very important in this organometallic chemistry. So and the counting of this rule is very important. So I have discussed several questions during this weekly problem solving session. So I suggest everyone, when you are doing the electron count, please follow the neutral method, because this neutral method is more convenient and more easy to calculate. Sometimes because of this charge on the metal center, the ionic method gives us to a wrong result. So it is always better to do the calculation in neutral method. Ionic method is also a good method, but somehow it becomes confusing. So neutral method I personally prefer more over this ionic method. So the calculation is simple. If we just need to know the number of electrons donated by a ligand and if the overall charge of the complex. If you have the overall positive charge, we just need to remove the electron, and if you have the overall negative charge, we just need to add electrons. So that's for example this molecule. So when there is more than one metal center, like this complex. So when we are doing the calculation for 18 electron, we will always do this calculation for one metal center. So we have 3CO, which is called the terminal, and we have 3CO, which is bridging. So the difference between the bridging and terminal CO is the number of electron donated to the metal center. For that, we need to know every ligand how many electrons are donated to these FT metal centers. So iron is 8 electron and one Fe bond contains the 1 electron, so gives rise to the total 18 valence electron. So for in this way we need to calculate. So we will not use to this positive and negative counterpart, so always use the neutral method for ligand L, which is more convenient and easy to get the correct answer. And the classification of these transition metal complexes has been done on their valence electron. So class 1 compounds are free to move, that is they have any number of valence electron, that is maybe greater than or less than 18. So the 18 electron rules is not obeyed for these class 1 metal complexes. For the class 2, we stop this 18 electron rule should be obeyed, or it should be less than 18 electron, not more than 18 electron. And for the class 3 complexes which exactly have the 18 electron in their valence shell. So this classification is very important, and depending upon the number of valence electron, we have classified these 3 types of organometallic compound and we have correlated their properties. I will explain this. So just for an example, let's say this example, copper. So how to calculate the total valence electron? So copper, we have the electronic configuration. Here copper is +2 oxidation state. So the 3D9 is the electronic configuration for this copper, Cu2+. So and here we have 6 NH2 ligand. So this gives to 9 electron and 6 NH3 ligand will give 12 electron. So total it will have 21 electron count. So this electron count we will do in the ionic method, as we have already considered the copper as a 3D9 system. But if you want to this calculation in neutral method, so we need to consider the total electron count of this copper. So for that we will have copper 3D10 4s1, that is here copper has total 11 electron and then 12 electron come from this ammonia, so D2 will give 23 electron. Now we have oral charge +2, so then we need to remove -2, which gives rise to our 21. So if we calculate the electron on the basis of neutral method, you can see that we don't need to consider the oxidation state of this metal center, which is more easy for calculation. But if you go for the ionic method, we need to know the oxidation state, and for corresponding oxidation state we need to determine the electron or valence electron in the. So this electron count is very important for this transition metal organometallic chemistry. This is the simplified MO diagram when we are considering only sigma orbital. So in sigma orbital we know that the sigma interaction only happen for NP orbital, S orbital and D orbital, where this D are dx square minus y square and dz square. So these total 6 electron in metal perform the sigma interaction. So for that we have this sigma, another sigma star and sigma star. So this is the 3 sigma star orbital we have, where this T2G has correspond in pi interaction. As there is no pi interaction or no pi bond or pi contribution from the ligand, this remains as a non-bonding. For that we have our delta O or T, the difference between the T2G and Eg star gives rise to our corresponding slitting energy. So when we have this similar situation with bi contribution, then the all other contribution, that is the sigma one of the sigma star and the sigma star remain same, but at we have this pi bond or pi contribution which will interact with the T2G sets of orbital. So the T2G will get lower down and we will have corresponding T2G star orbital. Now as the energy gap like the previous one increases, so now here delta O will also increases. So from this MO diagram we can clearly say that the ligands with pi acceptor orbital or ligands having the pi acceptor orbital will have the more delta O value. So from the MO diagram it is also very clear. Let's say for example, as we have seen that ammonia, and if we concentrate with CO, so carbonyl monoxide, so this will have the pi star orbital, so that will interact like this and this will increase the delta O value. Some square planar complexes having the 16 valence electron are also stable. As we have already said that 18 valence electron gives the most stability of the system, but depending on the geometry of the metal complexes, that is the number of coordination site, number of ligand attached to this metal is also depends on the stability. So some 16 electron valence complexes having the square planar geometry is also stable, or some linear complexes having the coordination number 2 is also stable, having the less than 18 valence electron. So with this we completed the general introduction or classification of the transition metal organometallic compound and their 18 based on their 18 electron rule. So as I said earlier that we have now moved to our first broad chapter, that is the transition metal bonded to a carbon where the carbon is sp3 hybridized. That is our chapter number 1 in this course, so which is called the transition metal alkyl complexes. So these are the three different types of bonding mode for these transition metal alkyl complexes. So it can be terminal alkyl, that is the MCR3. It can be C-center mu2 alkyl, or it can be mu2 alkylidene, or these three different types of bonding mode for these transition metal alkyl complexes or transition metal organometallic complexes where carbon have the sp3 hybridization. Different types of bonding mode has been shown here, which need to remember. So this is the vinylidene. There is some questions appear, or some questions and during the assignment topic, that the carbon atom hybridization of vinylidene. So this is the vinylidene. When we are talking about this carbon, so this carbon is generally the sp hybridization. So this carbon is sp hybridization. So hybridization of this carbon will be sp, so not sp2. So that this mode of bonding is called the vinylidene moiety. So here the hybridization will be sp, it should not be sp2. So then we have seen that the preparation of these transition metal alkyl complexes, here this preparation procedure is very important, where we are taking a diazo compound, where we know that the evolution of nitrogen is a highly efficient process to get this molecule. This is an important method or easy way to synthesize these transition metal alkyl complexes. Another methods are there which is equally important. Here this reaction is very important reaction synthesized using the acylation reaction, because if we have this acyl chloride, the chloride will divide and this acyl moiety will attach to this metal center. So simple in presence of HNU, that is in photochemical condition, again the removal of CO like the nitrogen gives rise to corresponding alkyl complexes. So as preferred complex CO elimination upon heating or radiation, which is gives this desired complex. So this is another important reaction. So next one is the oxidative addition reaction. So we have seen that oxidative addition happens to a transition metal complexes where it have the less than 18 valence electron. Here the iridium center have 16 valence electron. Also the oxidation state will be lowered. So for oxidative addition, we need to remember that oxidative addition will happen to a metal center where the metal's oxidation state is lower and also it has less than 18 valence electron. Sometime we will see in the subsequent slides that oxidation addition, this reaction does not change the oxidation state of the metal. This is also we are calling and just it will increase the overall electron count of this metal center. We will see it in next step. So oxidative addition is just basically the addition of a substrate and the metal center get oxidized to give an 18 valence electron, which is a important reaction. Or another point to remember that when this oxidative addition happen, this can be cis addition or it can be trans addition. So cis and trans both possibility is there during the oxidative addition reaction. So, so here you can see that the oxidative addition is happen, but the electron is have both 18 valence electron. So this is another general exception of our that oxidative addition always happen to less than 18 electron. So here we have the oxidatively add methyl iodide, that increase of oxidation state from +1 to +3, but the overall electron count remains the same. Now we are discussing the properties of this transition metal sigma alkyl complexes. Now the properties, when we are in terms of properties, that is the stability of these transition metal sigma alkyl complexes is, these complexes are sometimes stable or sometimes is undergo the famous beta elimination pathway to give the corresponding alkene molecule and the metal hydride. So the beta elimination is a very common decomposition pathway for these transition metal sigma alkene complexes. So beta elimination is if the corresponding compound or corresponding alkyl group are contain the beta hydrogen. So this is alpha and this is beta hydrogen. It will interact or undergo an agnostic interaction with the metal center, and because of this interaction we lose the metal carbon bond, and this hydride get attached to this metal to give the corresponding metal hydride and the corresponding alkene. That is a double bonded system. So beta hydride elimination is a common decomposition pathway for this reaction or for these transition metal alkyl complexes. So if this compound does not contain any beta hydrogen, there is no chance of beta hydride elimination. So this beta hydride elimination has been verified by this deuterium experiment, where we have the deuterated beta hydrogen which is eliminated that metal hydride, deuterated hydride and the corresponding alkene. So this is the experimental proof of beta hydride elimination. Now if our moiety does not contain the beta hydrogen, then that increase the stability. So when we are discussing the stability of these transition metal alkyl complexes, the main important part or in the reaction of stability, of course, so we should need to think about if there is a possibility of beta hydride or not. So if the possibility of beta hydride elimination is there, then the complex will undergo the beta hydride elimination rapidly and it becomes unstable or decompose easily. So this is a very good example of thermal stability. Of beta elimination reaction. So when the complexes sometimes does not contain the beta hydrogen, but it decomposes by a two-center two-electron decomposition or bimolecular mechanism pathway. So this decomposition pathway also important and it gives the stability of small or early transition metal alkyl complexes like the titanium, but corresponding the late complexes, that is the Pb6 is always stable in this condition. This is another very important point of these transition metal alkyl complexes. Here is some application or preparative method of these complexes, and when you are seeing unknown complexes, try to consider or try to calculate the electron count of these complexes, whether these complexes are 80 electron or not, so which will give you a confidence about the total electron count of different transition metal organometallic compounds. The CH activation reaction is another important application of these organometallic compound. Here you can see that the one of this PPH3, one of this phenyl ring on the is undergo this ortho hydrogen gets activated to form this metallocycle ring with the iridium. So this is the orthometallation reaction. So this reaction is another very important reaction here. So this is also called the cyclometallation reaction because we are forming a metallocycle here. CH activation reaction is very much important in organometallic chemistry, which gives the functionalized in different carbon atom. One important reaction here, this reaction. This gives the corresponding with this catalyst we have this reaction which is used in different coupling partners in cross coupling reaction. So as just now we have seen the CH activation reaction, the another activation, that is the CC activation reaction, is also important for these transition metal alkyl complexes. Now the activation of CC bond is very much challenging compared to that CH bond, though CC bond have less bond dissociation energy compared to corresponding CH bond. This is very need to important because the one thing is the statically demanding CH bond, because the number of CC bond is very less in a system, whereas in CH bond number are more in a system. Also, CH bond projects outside or outward of the system, whereas CC bond remain inside or core of a system. So reaching or to activate, we need CC bond, we need to go inside of a molecule, so which indicates that the pre-coordination is difficult for transition metal. So that's why CC bond also get activated in different transition metal alkyl complexes to give value added product. So I will not discussing this in detail. So this is the main point or main important feature to active any CC bond or any bond. So first we need to CC bond should, any bond like XX should undergo the coordination to the metal, and then the metal which weaken the sigma donation of this XX bond, and then the metal donates electron to this sigma star or pi star orbital through the back donation, which decrease the bond strength to for the subsequent breakage or cleavage of that bond. This is the different types of bonding interaction of cyclopropane and alkene system. So we have all discussed these activation reactions in detail. So we can say that this dissociation energy of H for the phenyl ring is lower, corresponding to that CC bond in PHCH3. This is PHCH3 and PHH. So this is a very important point. So generally we have seen that the CH bond dissociation energy is another activation of these transition metal fluorocomplexes. As fluorocompounds are more robust, so their activation requires are challenging. One thing to these metal fluoro complexes is that these complexes are, because of the high partial charge on the metal, because of the highly electronegative fluorine ring, this alkyl moiety becomes highly negatively charged, which creates a high positive charge on the metal center. So this creates the metal alkyl or metal perfluoro bond is more strong compared to the metal normal alkyl bond. For these perfluoro complexes, one thing is very important to note in this section is the reversal of polarity. So, as we can say that the halogens are generally electronegative in nature, but because of this perfluoro alkyl moiety having the high electronegativity or high partial negative charge on it, this become delta negative, which creates a delta positive charge over the, so this is called the perfluoro iodide. Perfluoro iodides. This is a very special case. So now, as because of the high negatively charged of this perfluoro moiety is undergo the nucleophilic attack with carbonyl metalates. No electrophilic attack, no perfluoro transition metal bond. So because of this, only this is for not metal alkyl complexes, not metal alkyl complexes or perfluoro alkyl complexes is formed. It simply undergo the dimerization reaction to eliminate this. So this reaction is very important reaction, that is the reversal of polarity of perfluoro alkyl complexes. These are the similar reactions of perfluoro alkyl complexes. This bond energy just need to remember or with respect to the carbon hydrogen, carbon and carbon fluorine bond energy. So carbon fluorine bond energy is highest and the carbon bond energy is lowest. So here one question is important, that instead of low carbon bond energy corresponding to the carbon hydrogen bond energy, the activation of CC bond is more challenging compared to the CH bond. This question is very important question, and anybody need to know the answer of this question in more detailed way. Now with that we move to another system, that is our next system, that is a transition metal alkynyl complexes or aryl complexes. So if we have, so sometime we call it as a transition metal CsP2 complexes having the carbon atom sp2 hybridization. So for these transition metal alkynyl complexes, this restraint of stability is very important. Where the transition metal allyl complexes is more stable compared to the alkynyl or compared to the alkyl. So only because of this electronegativity, that which I showed in the first slide of today's discussion series, that the alkynyl, that is the carbon atom having the sp3 hybridization, is most electronegative compared to the sp2 and the sp3, so which also gives the more stability of this system. Another very important complexes for this sp2 category or sp2 stream is the transition metal carbene complexes. So carbene, we know that as neutral bivalent species which have the electron, which are electron deficient in nature. Because of this electron deficient, and the Fisher and Shor discovered these two different types of carbene system bonded to this transition metal. Generally, carbenes are reaction intermediates and they are highly unstable. But the presence of the heteroatom adjacent to this carbene carbon brings the stability, or also it performs as a ligand to the transition metal. So we have two different types of carbene moiety which act as a ligand to the transition metal, where the carbon atom is sp2 hybridized. So one is transition metal Fisher type carbene, another is shock type carbene. The Fisher type carbene is when the carbene atom present with adjacent to an heteroatom like oxygen, nitrogen or sulfur. These are called with only one heteroatom or at least one heteroatom adjacent to this carbene moiety is called the Fisher type carbene. And when these complexes have without any heteroatom, it only have the carbon atom or hydrogen substituted adjacent to this is two hydrogen substituted. So we call them as a shock type carbene. So, and this, because presence of the heteroatom also creates the reactivity or the properties of these two carbon center. Because of the heteroatom, this carbene, Fisher type carbene, become electrophilic in nature, whereas this shock type carbene, because of this hydrogen or carbon atom adjacent to it, is become nucleophilic in nature. There are different procedures for their preparations. as carbons are highly reactive in nature, and when this carbene carbon is present adjacent to these two nitrogen moiety, we call them n heterocyclic n heterocyclic n heterocyclic carbene, that is NHCs. As thus, if we have very small substituted on this nitrogen atom in under normal condition, this carbene carbon easily undergo dimerization. But this dimerization is only irreversible and it does not dissociate to give the free carbene. So this is you need to remember. So the way of dimerization is a irreversible process. We can generate these reactions in different types. Arduino first isolated this or stabilized this carbene with that bulky adamantyl substituted, which have the melting point to 40 degrees centigrade, and these carbenes are highly stable under normal condition, and this is also not undergo the dimerization because of the steric bulk of adamantyl ring, and these act as a transition ligand to transition metal C with sp to hybridization, transition metal carbene complexes. These are the different. The carbene can be two spin multiplates. One is singlet, another is triplet. So singlet is when the two unpaired electron resides in a same low, and triplet is two different electrons reside in two different low. In spite of having different electronic configuration, we have to remember that both the carbene is sp2 hybridized. Reactivity of this carbene is very simple, and so there is no need to discuss in detail. These slides is a very important slide regarding the characterization data of transition metal carbene complexes. Now, as we have seen that the electrons on this carbon atom are donated to the metal, that is tantalum or other metal or chromium. Here, these carbon atom become highly de-shielded in nature. So this ppm value is clearly indicate how much de-shielded this carbene carbon is. So as these are called the shock type carbene. These are called the shock type carbene, which act as nucleophilic in nature, whereas the heteroatom stabilized carbene, that is the below one, as Fischer type carbene, which resonates at a more higher field, and also it gives electrophilic reactions. So the carbon NMR shift or de-shielding nature of carbene carbon also disclose its reactivity. This is also an important reaction. That carbene complex are core source of free carbene. This thing you need to remember. As I said that carbenes are free carbenes are easily trained to dimerize to give the corresponding olefins, but these olefins are not dissociated to give the free carbene. So the source of free carbene is very rare. Also, when the carbene also the carbene ligand when it is binding to the transition metal not undergo the carbene transfer agent. So sometimes the complexes also not a good source of carbene transfer agent. But here we have a very good example where this carbene moiety is transferred to this ring to from this cyclopropane ring. So this is another very good or important example of carbene transfer agent. So these moiety act as a carbene transfer agent, whereas we rarely see the transition metal carbene complexes as a free carbene transfer agent. These are the preparative method for. So similarly, carbene, and we have another complexes which is carbene, having the triply bonded to the transition metal, carbon triply bonded to the transition metal. So one of the preparative method for these carbene complexes is the alpha deprotonation. So the simply carbene complexes can be prepared from its corresponding carbene complex can be prepared from its corresponding carbene complex. So if the carbene complex give the corresponding carbene complex. This is a very easy method for preparation of these carbene complexes. This is another example of this. So here we need to discuss or know the structures and bonding of these complexes. Now this is a very good complexes or DNP tungsten CH2CMe3 CHCMe3 CCMe3. So here we have all three types of bonding mode in a single complex of tungsten. So you can see that we have first transition metal alkyl complex having sp3 hybridization. We have second transition metal alkynyl complexes or carbene complexes having sp2 hybridization. We have transition metal carbene complexes having sp hybridization. So and these complexes also structurally characterized. So in a single complexes where we have three different mode of bonding and the bond distance are below. Obviously the alkyl bond will be more longer corresponding to the alkyl, that is the sp3, sp2 and sp. So and the alkyl bond will be shorter. These complexes are very important topic to remember. Like the carbene, we have the carbene have singlet or triplet spin state. Also, this carbene have doublet or quartet, and the spin state arises from the rule 2s plus 1. That is, if it is 1, 2, 3, 4. So different number gives the different spin state. For 1 it is singlet, for 2 it is doublet, 3 it is triplet, and the 4 it is quartet. So we the number of unpaired electron, that is the S value, generate the total spin state of the molecule. I have already discussed this in this weak problem solving in more detail. So this spin state is coming for singlet, triplet, doublet, quartet, coming from this formula. This is the bonding pattern, which is again the same like the others. Transition metal carbonyl complexes. Next, another ligand having the sp2 hybridization bonding to this transition metal. So these are the different general methods for preparing different transition metal carbonyl complexes. So carbonyl complexes, as we know that, have different strong pi accepting property. Because of the strong pi accepting property, these complexes are sometimes become highly stable in nature, and these are also the different types of structures of the complexes can also be characterized by So some of these transition metal carbonyl complexes structures is very interesting, and these structures you need to remember for exam point of view. Like this structure Mn2 CO10, this structure, and then similarly cobalt complex of the carbonyl. The number of bridging CO and the number of terminal CO is very important. Also, as I have mentioned that for higher more than 3 number of metal center, the possibilities of bridging is very less for the heavier transition metal like the rhodium or iridium, and this bonding of this transition metal can be possible through this eta 1 type of bonding, eta 2 type of bonding, also the eta 3 type of bonding, but 4 metal center bonding is not possible for this. we have seen one question from this. Also, this complexes of this cobalt is very important because it shows a dynamic equilibrium. So in the solid state we have this solid structure, and this structure exists in the liquid form. So in the solid state we found the carbonyl bridging, whereas in the liquid state we found the only terminal carbonyl. So this structure of this complexes is very much important. So few structures is of this metal carbonyl you need to remember for determining the exact number of terminal and bridging CO from exam point of view. This is the different mode of bonding for these carbonyl complexes, and bonding property is very similar, that it has two types of bonding, as is the sigma bonding and pi acceptor bonding. And this bond order you need to remember, as I discussed this question in I think second class, that is the week 10 or week 9 one of the series, in very detail how these bonding interact. So if we have a metal is bonding to CO, now if the metal is highly electron rich, or that is the metal attached to the ligand which is highly electron donating, then metal will transfer electron to this carbon, which will decrease the bond order of CO. So metal carbon bond order will increase, and the metal carbonyl bond order, the CO bond order, will decrease. So, but if we have where the Ln or L is electron rich, but if we have the another ligand attached to this metal where the ligand is highly electron withdrawing in nature, let's say another pi acceptor ligand, then these withdraw the electron from the metal. So for that case, this electron density on the oxygen will again transfer to more to this carbon, which is increase the sigma donating property. So there the carbonyl stretching frequency or the carbonyl bond order or bond strength will increase the higher stretching frequency corresponding the bond order. So depending upon the carbonyl stretching frequency, we can give a brief overview of the metal carbon bond strength, or the different type, interpret the different types of sigma donating and pi accepting ligand present in the system. So the bonding is very important. So it donates through the sigma bonding and it accepts the electron in a pi star orbital. I also shown the MO diagram in second last series. So here this series is very important. You can see that clearly that the increasing, that the higher staging frequency is decreasing. If you say from left to right, higher staging frequency increasing. How it is increasing? So here it is relatively proportional to the number of electron density on the metal center. So metal center have the negative charge, and this negative charge -1, this is neutral, and this is increasing the positive charge. So as metal center increases the positive charge, that means the more sigma donation is happening from carbon to the metal. So as I have already just now discussed that the effect of sigma donation will increase the or effect of sigma donation will strengthen the CO bond. So if the CO bond become more stronger, then corresponding the IR stretching frequency will be less. It will be also increases. More strong bond, more strong IR stretching. Also, in the way they are saying that increasing pi acceptor interaction. So as the electron and negatively charged increases, so the pi acceptance property of the carbonyl is increasing. So metal is pushing more electron to the pi star orbital. So for that, with the number of increase of negative charge on the metal center, that is the increase of electron density on the metal center, also decrease the stretching frequency. The increase of electron density on the metal center is mainly pushes that extra electron to the pi star orbital of the CO, which eventually decrease the bond strength of CO and the stretching frequency of carbonyl. So this is a very important fundamental things of IR stretching frequency to understand for metal carbonyls. Trends. Also, as the number of metal center increases, the IR stretching frequency also decreases. So this free CO, these values you need to remember that free CO have the stretching frequency of 2143 cm inverse, and when it undergo a different binding mode to the metal, the corresponding stretching frequency decreases. This trend is also follow here. So bonding I have already said, and the number of CO band depends on the geometry of the complex. Number of IR band observed in a molecule is also depends on the geometry, that is the overall symmetry of the molecule. As the symmetry decreases, the number of IR stretching band also increases. So there is, I have provided a particular chart on our on this session. You can check out this. If you have any doubt, you can ask me later on. So with this is I think enough for this transition metal carbonyl chloride, halide, or transition metal carbonyl hydride complexes. So this is the corresponding thing. Also, that when we have an hydride attached to the metal, only possible to characterization through NMR is that hydride appear in the 1H photon NMR at highly shielded region, generally -5 to -50 ppm. It is a highly large high field region. Also, we have different value of hydride coupling in different metal center. This is called a very important reagent in synthetic or organic chemistry is called the Coleman reagent. This Coleman reagent is nothing but the Na2FeCO4, where you need to know that iron resides in Na plus and FeCO4 2 minus, that is the iron resides in negative. So when these complexes is reacting with a simple alkyl halide, these undergo the addition of an alkyl moiety to this iron center, which any substrate the D gives the moiety as our product. So when this is the highly intermediate and these intermediate transfer to different value added product under different condition. See, if you have an RR, it will give the, and here the carbonyl migration or alkyl migration is the key part of this synthesis. So it gives that ketone, and then if we have the carbonyl, we also get this acyl substituted moiety, which further gives the oxygen present give the corresponding acid. Also, if we react with the halogen, it gives the corresponding acyl chloride, which can also gives the corresponding amide. So with this reagent, that is the Coleman's reagent, with different alkyl halide or acyl halide, we can transfer it to different value added product. So this Coleman reagent is very important for synthetic organic chemistry, and these undergo the alkyl transitional alkyl complexes, which carbonyl undergo the carbonyl transfer reaction or migration reaction. This is an example of these two. Also, that this reagent is functional group tolerance, that is, it does not hamper as any other functional group. So that is another importance or application of this molecule or this reagent. Now we have only our last series, that is the transition metal complexes with olefin ligands or conjugated olefin. So butadiene is another conjugated olefin. So here Psi1, Psi2, Psi3, Psi4 are the 4 molecular orbital diagram, and 4 molecular orbital diagram perform different types of interaction with the metals, with the different metal orbitals. So this is the order of energy. This is the energy order, and also for the Psi1, if we have the number of node, node equal to, I have already said that n minus 1. N minus 1 is the number of node. So node represents where there is no electron density in the system. These are the different types of bonding mode. So here one thing to remember, that when their binding mode is like this terminal binding or these types of bonding, they are having the 2 electron donor. When they are act as electron rich. When and these types of binding where they are a bidentate mode, they act as a 4 electron donor, and this is for the electron poor metal fragment. This binding mode is very important. Again, we can say that the more than 2 metal center binding or 3-4 metal center binding is not possible for these systems. And this is the terminal binding or side-on binding for this reaction, where the CC stretching frequency is 2088, which also decreases from the original CC stretching frequency, indicates that bonding of this. Because of the steric bulk of this tertiary butyl group, this angle decreases from linear 180 angle and also angle. So these alkene act as a 2 electron donor. This is another, this here all this reaction, like this reaction, again this reaction. You can also follow my last week 12 PPT or week 12 question. Here all the reactions are very important types of reaction, because different kind of substrate or so generally for these early transition metal like the titanium and all, the formation of this cyclopropane type ring is more facile, and for the late transition metal like the platinum or palladium, this formation of terminal mode is more facile. So with this, I think I came to the end of this today's discussion series. That is, here I have not discussed any new questions, just pointed out some important topic or important reactions which has been discussed in this course. If you have and here any doubt, you can ask me. I will try to answer. Another important reaction for this last series is the Bonnemann cyclization reaction. Here the importance of this reaction in industrial purpose, because we can make 2 substituted pyridine, which, as we know that pyridine is an important molecule, and in organic synthetic chemistry also this coordination chemistry, and but the substitution on the pyridine in the 2 position is highly challenging because of the electron circulation in the pyridine ring. So this method gives a substituted pyridine in very high yield. So this reaction of Bonnemann cyclization reaction using our cobalt, a simple cobalt catalyst, that is the COD. So this is a simple cobalt catalyst can undergo the cyclization or the cyclization reaction of an alkyne and nitrile. So alkyne and nitrile undergo cyclization or cyclization reaction to give the substituted pyridine. So this reaction is very important reaction in synthetic chemistry, as the challenges are to substitute in this pyridine 2 position is highly difficult. So I think I have covered most of the important topic of this series. So in this course, we have learned the classification of transition metal organometallic complexes depending on their valence electron, that is 18 valence electron rule. We have learned how to count the total valence electron, and then we have seen the three major types of ligand bonded to the transition metal to form the organometallic compound. One thing is the transition metal alkyl complexes, that is the carbon atom is hybridized in sp3. Another is transition metal alkyl complexes where the carbon atom is sp2 hybridized, and then lastly the carbene complexes where carbon atom is sp hybridized. Instead of this, we have also discussed the application of these transition metal organometallic complexes like Coleman reagent, this Bornemann reaction to different important inorganic and organic synthetic chemistry to synthesize different molecule which are challenging to synthesizing in without catalysis. From transition metal olefin complexes, we have seen that some complexes or some compounds are highly unstable, or mainly the olefin complexes are highly unstable or explosive in nature, but when they are binding to transition metal they become highly stable and that can be used later on. So there are several applications of this transition metal or organometallic complexes and their different ligands. Also, we have discussed the CH activation reaction and CC activation reaction and C perfluoroalkane activation reaction in introduction to move in detailed way and their application in day-to-day life. If you have any question from this previous week question answer series, or if you have any question to overall this course run, you can ask me. I will try to answer it, or if not, then I will close this session now. And today is the last day of this interactive session. So I completed the week 12 session in the last week, taking one extra class on 6 October, so that it will be more convenient or easy for the learners to revise all the weekly question from the total assignment as well as the assignments from this live session for better understanding the course. And today I have taken this class as the doubt clearing as well as the extra session to summarize this course content and to increase and the important topics or important chapter in this course. So if there is no question, I thank everyone to joining this session. If you have any question, you
हेलो सर.
हाँ
सर एग्जाम में नेगेटिव मार्किंग है क्या?
exam negative marking, I think negative marking is there. I am not sure.
Okay sir.
I am not sure about the negative marking, but maybe it will be there.
Okay sir.
So exam is
Okay sir.
Exam is 26, right?
Yes, sir.
Yes sir.
So I think there will be a live session from the professor. So if you have any doubt from this exam session, you can directly ask him. He will clarify. if you have any doubt regarding these lectures today, you can ask me, or I suggest go through all the questions, that the assignment question as well as the questions which I discussed, so that you will get an
So can we get this recording of today's meeting?
hello.
So can we get the recording of today's meeting?
Yes, actually all the recordings whichever session I have taken, there will be a recording sheet in the portal. Also the recording sheet is sharing in the feedback form through the email, so you can get all the slides. Slides is basically consisting of the questions which I discussed in this session. So if you just go to that drive link, there is a recording sheet there is, and you can get the recording of all week 1 to today is week 13. So all this recording video in the YouTube you will get it, and also the slides, that means the questions which I have discussed till the last week, that is the week 12. So you will also get that in the drive link. Okay.
Okay, sir. Thank you, sir. Thank you.
So don't worry about if you are not able to join any other session.
Yes.
So for better performance in the course, I ask, or I please go through the questions, from all the questions, and try to understand
Yes,
the
sir.
questions or logic behind the question, so that there is nothing difficult. This chapter everything is easy, but I think, or I believe, some reactions are very difficult to remember, but from the chemistry point of view, the logic behind this is very basic, and you can remember it without any other disturbance, or it is not difficult, I can only say. So I hope the best for the exam, and
Thank you.
I mainly ask to, before going through the slides, lecture videos and all, please go through all the questions, assignment questions which are in the portal, also the questions which I discussed in the series, that is the week 1 to week 12, so that you will get a broad idea. One thing I want to mention, that vinylidene, there is a question was asked during this live session, the hybridization of the carbon atom of vinylidene. So it will be sp hybridized. It is also there in the portal assignment. It is not sp2 hybridized. So vinylidene carbon is sp2 hybridized. Today I also show in the slides that it is sp hybridized, not sp2. So for best reference, you can go to this book, Christopher Elsenbrois, organometallic. It is also available in internet. You can freely download and go through it. For most of the questions or most of these references from that book. And another book is Robert H. Capti, organometallic chemistry book. You can also go through that. I will suggest go to the Christopher Elsenbrois book. That will be more helpful from exam point of view. So 26 will be the exam, I think, for this course. I hope best of luck for this examination, and thanks for watching and joining in this session. If you have any other doubt regarding this or exam pattern, you can post in the discussion forum, so that we will answer it subsequently. Thank you for joining. Any
Thank
other
you, sir.
question is there?
Thank you, sir. No, sir.
Okay, then thank you for joining. You will get this recording after few hours. I will upload it. Also, we can show the previous recording of that recording sheet. Okay, thank you for joining and watching.